Hello and welcome to this demo about on-demand key distribution for cloud networks. My name is Nikolai Paladi. I am a senior researcher at Lund University and write cybersecurity. The citizens of modern cities are increasingly interconnected among themselves and with the cities in which they live in. First and foremost, they are interconnected using the almost ubiquitous mobile phones or smartphones, but they are also increasingly interconnected using other wearable devices. We see a similar picture in the city infrastructure. So for example, the electric vehicles or the public transport might be interconnected with the other services of the city for surveillance and security monitoring purposes, as well as for monitoring the status of their electric batteries or the status of their engines. A similar picture is in the built environment. For example, the built environment is routinely monitored for security reasons as well as for utility reasons or safety. For example, fire alarms, ventilation, heating and water supply, all of these are increasingly monitored remotely. Typically, all this data would be collected locally and sent to a cloud backend for processing. However, it has become increasingly evident that the growing volume of data cannot practically be sent in its entirety to the cloud backend, and so instead the cloud edge paradigm was born. Our data is first pre-processed as close as possible to the source. It is normalized, filtered, and reduced to a smaller amount, and then it's further sent to the cloud backend. So let's now see what is contained in this edge computing box. It would typically contain an orchestrator. So this is a component that is to set up all the other components and manage the data flows between the different components in an edge node. Typically, it would set up a software switch or virtual switch that would connect or interconnect the monitoring or the data collection devices, the data source devices, and send them for processing to some edge backend, which would be perhaps a Docker container or similar. The orchestrator would also set up a network controller that would control the data flows between the data sources and the processing and backend. The network controller typically communicates with the software switch through a standardized protocol. OpenFlow is one such standardized network management protocol. So finally, data collected from the different devices would be sent to the edge processing backend, where it would be processed perhaps using a machine learning model, and then the inferences be collected and then sent further to the cloud backend. So how can we address some of the challenges in this image, some of the computational challenges? One of the major challenges is ensuring secure on-demand communication between the connected devices that collect information, collect data, and the edge that processes it. To address this challenge, we have designed the on-demand key distribution protocol such that metric keys are distributed on demand between the connected device and directly the processing end. In this scenario, for example, each data source can obtain its own key pair, symmetric key pair, that would ensure security of its communication directly with the edge backend. So let's see how it works in more detail. So let's say we have a client and the server here, and the flow between the client and the server is monitored or is established using a network controller, and here we have the orchestrator as well in the picture. So the client first sends a transport layer packet to the server to just establish a transport layer connection, such as TCP. The virtual switch would check whether it has any rule that matches the flow between this client and server, and it would detect that there is no such rule. So in that case, the switch can upstream the packet to the network controller and let the network controller decide what to do with this packet. So actually what the network controller decides is that, okay, this is a client and server that both support the protocol, and so we will distribute a pair of symmetric keys to the client and the server through the orchestration channels that the orchestrator anyway has with the client and the server and maintains for monitoring and logging purposes. So the same channels, the same secure channels, are used to distribute these keys to the client and the server. And at the same time, the network controller returns or pushes the packet back to the switch, installs a respective rule in the rule table, and the switch forwards the packet to the server. The server, having already a shared symmetric key with the client, uses this symmetric key to encrypt the future communication. Once they arrive to the TLS level, to the TLS protocol layer, the server uses the symmetric key to encrypt the data and send it back to the client. In a nutshell, that is the entire idea of the protocol, and now I will show you more in the demo. Welcome to the second part of the demo of on-demand key distribution for cloud networks. Now that you're familiar with the wider context and the background of this work, I will show you a short demo of our implementation. It's always tricky to show the demos of backend services, but I'll try my best to do that. So we have a couple of panes open here, and this one is the first one, and I will just launch the script Flowrider example from here. So this script sets up several network components. In particular, it sets up the network controller and the two endpoints that will be communicating, as well as a network switch, and does some additional network plumbing in between. So next, I'll just follow the instruction in the README, and I will launch the endpoints. First, we launch the containers for the endpoints. So I'll do this one by one. Docker attach Flowrider 2. So this is the server that will be running the server, let's say, application. And we start the key server that will receive the key from the network controller. So this is the server that listens to the key that will be distributed to it from the network controller, according to the protocol that we described or that we introduced in the demo paper. And likewise, I open another shell to the same container in order to run the server that will be listening, the application server that will be listening to the incoming connection. So this little server is listening to incoming connections and accepts the files that are sent to the server. Next, I'll take care of the container on the client side. So let me start it. I attach the client container called Flowrider host 1. Sorry, we don't attack it, we attach it. Then I go to the endpoint directory, and likewise I start the key server. The key server listens to the keys sent from the controller. So it's always there, ready to receive the keys that are sent from the controller. And finally, I attach the last shell to the client container. So here we go, same to the endpoint. And now I'm ready to launch the client application that will send over a file to the server application running here. So I will, to make it easier to inspect later on what has happened, I will pipe this to a demo file, and so later on we'll check it out. So here it goes. Now what you've seen is that at some point, so as soon as I started the client, called the client command, the packet reached the virtual switch that didn't have a rule what to do it, so it upstreamed the packet to the controller.
the controller recognized that this is a packet coming from a client that is supporting our protocol, and so it distributed symmetric keys to both the server container and the client container, so to the key servers on both the server and the client. You can see here got a connection from, this is the controller that distributes the symmetric keys, and then the two endpoints, the client and the server, use the symmetric key to negotiate a key for their TLS connection. Now let's examine what actually happened. So let's see the demo.txt file. Not very exciting, a lot of log files from the TLS negotiation that is happening. So server hello was received as expected. They generate the pre-master secret, change some variables, generate a key and an initialization vector. So that's usual TLS. And then the client sends the data to the server, so it sends the contents of the file to the server. Once that is done, it's a long file. So once that is done, the TLS connection is closed, and we get an all done log message. So all in all, what you've seen is the flow of how the protocol works. It's actually very simple, and it relies on the fact that the network controller has certain knowledge about the topology of the network that it controls, that it operates in, and that the two endpoints, they might communicate very often, and we don't want them to use a whole lot of CPU to generate keys using their using asymmetric cryptography, or they might not even need to support it, and instead we use a symmetric cryptography that requires a smaller and simpler code base to use, and also facilitates the patch management and other aspects, other operational aspects. I hope this was clear, and I'm now looking forward to your questions. Thank you for your attention. Bye.